Precipitation process. This is lecture number 2. We're going to introduce 3 ways to produce precipitation. And in all 3 ways, what you've got to do is you've got to get warm and moist air at ground level, and somehow you've got to get it lifted into the troposphere and cooled to dew point. Now, here we've got an outline showing the 3 ways, and it's going to take a few lectures to get through these 3 ways. Now, in this lecture, we're going to go into the details of convection or convectional precipitation, and it represents the spontaneous rise of heated bubbles of air. And here it is illustrated here. Convection means vertical movement of air. And actually, I've already introduced convection when I was talking about that example of creating a hot spot over Nichols campus and getting it to rise to dew point. Now, we're going to go over the details of convection because sometimes convection just simply can't happen. Now, in the next lecture, number 3, we're going to talk about orographic precipitation, illustrated here. Now, orographic refers to mountains, and in this case, it's the forced rise of warm, moist air, and you get it to rise in the troposphere at a tall mountain barrier. Now, of course, we don't have mountains in Louisiana, so it's not a factor here, but it's very common in the western United States. And then eventually we'll get to frontal precipitation. And again, this is the forced rise of warm air at a frontal boundary. And this is a very common way for us to get precipitation in wintertime in Louisiana. So we'll eventually get to that. Well, let's do convection, the details of that. All right, convection represents afternoon thunderstorms. And it's very common in Louisiana during the summers, and it's the main way we get precipitation in summertime. So usually it kind of begins in May and through September, and is usually pretty much done by October, in the southern United States. All right. Now, in order to introduce convection, I've got to talk to you about something known as lapse rates, and these are rates of temperature decline in something. And the first one I want to introduce you to is called the environmental lapse rate. It's a mouthful of a term. We abbreviate it ELR. Now, this is the rate of temperature decline in the troposphere. You've seen this graph before when we were talking about temperature and introducing the troposphere. And of course, it's defined by temperature decline. And there is a world average. On average, temperatures decline in the troposphere about 3.5 degrees for every 1,000 feet you go on up. And so we're going to be talking about the actual rates of temperature decline in the troposphere, and it varies. And I want to make the point right now, and you'll understand it just a second, but this is for still unmoving air. This is not the rate of temperature decline in that heated bubble of air. And so it's just, what is the temperature in the troposphere at 1,000 feet? What is the temperature at 2,000 feet? Now, there is a world average. So what that indicates that the rate varies. And I want to go over, why the rate can be higher than the world average and why the rate can be lower. And the rate of temperature decline in the troposphere, the environmental lapse rate, is really kind of a seasonal thing. It depends on the temperature of the surface. So, during the summer months, when the surface is superheated, just think of Louisiana. We've got 90-degree days for several months. I've got the troposphere here, and I've added some lines. Here's 80 degrees, 90 or 100 degrees. But so we're super heated at the Earth's surface, and what that means is we're going to have very large rates of temperature decline in the troposphere because the surface is superheated. So rapid rates of temperature decline. And so it wouldn't be uncommon around here to have, the environmental lapse rate be something, much larger than the world average. Something like maybe, 6 or 7, 8, 10, 12 degrees temperature decline per 1,000 feet. And we're just going to use a nice, easy, rounded off number because I'm going to use an example of when convection, can't happen and when it can. And we're going to be using the environmental lapse rate in summertime, and we're going to use it, this typical rate of 10-degree temperature decline for every 1,000 feet in summertime. Now in wintertime, the winter season, it's cooler, freezing 40, 50, 60 degrees. So in general, the temperature, is much cooler at the Earth's surface. And so, it's cool at the surface and it's cool aloft. So rates of temperature decline are much less when the surface is already chilled. And, a typical rate for us around here would be, maybe, 2 degrees, 3 degrees, something like that. For every 1,000 feet you go on up. So a much lower rate of temperature decline since it's already cooler aloft. And we're going to use these numbers. We're going to have a wintertime example when convection can't happen, and then we're going to have a summertime example. And we're just going to use these numbers in our example. Now there is another lapse rate I've got to introduce you to. And it's, again, a mouthful of a term. It's Latin. It's called the adiabatic lapse rate. And we've got a different lapse rate now. This is the rate of temperature decline in that rising bubble of air. In the rising bubble of air. And there are two kinds of adiabatic lapse rates. Now, this first one is called the dry adiabatic lapse rate. And we just abbreviated DALR. Now, this is the rate of temperature decline in that bubble of air, in that thermal, as it's rising before we reach 100% relative humidity. It's the rate of temperature decline before dew point is reached. Now, this is a standard worldwide rate based on air pressure. And so the rate of temperature decline in that rising bubble of air, once it lifts off the ground and rises 1,000 feet in the troposphere, it's going to decline 5.5 degrees for every 1,000 feet it rises until we reach 100% relative humidity. Now, the second type of adiabatic lapse rate is called the wet adiabatic lapse rate, adiabatic, and we abbreviate it WALR. Now, it's called the wet adiabatic lapse rate because this is the temperature decline after dew point is reached. This is when condensation is occurring. We still have the thermal rising and cooling, making the cloud. And so we're actually, we're actually forming the cloud. And so we've got its own rate of temperature decline. Because the phase change is occurring, you're going from water vapor to actual water droplets. And actually heat is released. And so the rate of temperature decline is less than 5.5. Now, it varies depending on the amount of moisture in the air. But a typical wet adiabatic lapse rate would be something, between a temperature decline of 2 or 3 or, 4 degrees for every 1,000 feet, making the cloud. So we're going to use all three of these lapse rates, the rate of temperature decline in the troposphere, and then we're going to compare it to the temperatures in the rising bubble of air. Now, what we're going to do is we're going to do two examples. We're going to have a winter day, and just imagine South Louisiana. Now, in winter, we do not have convection. It just doesn't happen. Now, what I'm going to do is a table, and we're going to move. It's going to have 3 columns, and we're going to move upwards in elevation or altitude. Now, the first column is going to be the elevation, and we're going to start at the ground level, and we're going to move up in 1,000-foot increments because that's what these lapse rates have. And then the middle column is going to be the environmental lapse rate on this winter day. Now, we're just going to say it's, about 60 degrees outside at the ground surface. And remember, it's winter time, it's cool out, and it's cool aloft. So a typical environmental lapse rate in the troposphere would be a low number. And we're going to just use that 2-degree rate of temperature decline that I gave you for, typical winter season around here. And then we're going to say in this third column that a hot spot forms. And we've got a heated bubble of air that wants to lift off. We've got a thermal that wants to rise, right, and cool in the troposphere. Now, so right here at the ground, I've got a heated bubble of air. Now, I just added 2 degrees. It could be 5 degrees or anything like that. But I just wanted to show that we have a little hot spot that's formed. Right? Now, it's going to lift off, and it's going to cool at its own rate, according to the adiabatic lapse rates. Now, it's going to lift off at the dry rate. Which is a standard worldwide rate of 5.5 degrees temperature decline for every 1,000 feet. So what we're going to do now is we're going to move up 1,000 feet, and we're going to compare the temperature in the troposphere at 1,000 feet and the temperature in the rising bubble of air. All right, and so we're at 1,000 feet. Now we've got a low rate of temperature decline, a small rate in winter time. So we're just going to subtract 2 degrees. So the temperature for still unmoving air at 1,000 degrees, we've only dropped by 2 degrees. Now, in this heated bubble of air, we've got to subtract a larger rate. Right? The standard temperature decline, according to the adiabatic process, we've got to subtract 5.5 degrees from our heated bubble of air. Now, that's a larger rate of decline. And so already at 1,000 feet, our once heated bubble of air is no longer warmer than the surrounding environment. It's cooler. And what does cool air do? Does it rise? No, it sinks. Now, I'm going to somehow make this bubble of air make it to 2,000 feet. Now, I don't know how it does it. It's going to resist lifting. And we're going to stop it here. But again, so what we're going to do is see, all right, the temperature in the troposphere at 2,000 feet, we're just subtracting 2 degrees, small rate of temperature decline, it's cool aloft. And so the temperature in the troposphere is 56 degrees. All right. Now, in the heated bubble of air, we've got to subtract it according to the adiabatic process, in rising air. So inside that bubble of air, we've got to subtract 5.5 degrees. Right? And so now let's take a look at the temperature in what was once our buoyant bubble of air that spontaneously wanted to rise compared to the temperature in the troposphere. It is now colder than the surrounding air. Colder. And what does cold air do? It sinks. There is no way that this thing is going to make it to 3,000 feet. I don't even know how it made it to 2,000 feet. The condition, all right, that this situation represents is known as stable air or stability. Right? The condition on this date, all right, means that the bubble of air becomes colder than the surrounding air, right, and it resists lifting and ultimately sinks. And what do you know about pressure and sinking air? All right, and so you've got a whole bunch of these little hot spots and thermals that want to rise, hundreds or thousands of them in an area, and they're starting to rise, and then they're all sinking and sinking and sinking because they wind up becoming colder than the surrounding air because the environmental lapse rate is so small compared to our larger rate of temperature decline. And so this represents high pressure. And so this is why when we have high pressure, we've got cloud-free conditions. This is something that was talked about, in the material for exam 1. High pressure is usually cloud-free. And this is it. All right, there's no clouds, and if you've got no clouds, you've got no rain. Because usually that bubble of air is going to start to sink before you reach dew point. All right, it's going to cool. Right, and you're never going to reach dew point. If you don't reach dew point, you don't make a cloud. Right, and convection cannot happen. So there is another very important term you need to know, and that is stable air. Right, and that is associated with high pressure. So when we've got high pressure, the condition is stability. Right, and the air is sinking. Right, and we have no clouds in clear conditions. So convection cannot happen. Now let's do convection. Let's have a steamy, hot summer day in South Louisiana. Now we're going to go much higher up in the troposphere because we are going to have convection. we've got the same three columns. We're going to go up in 1,000-foot increments. Now it's summertime, and the surface of the ground in South Louisiana is pretty hot, and so we're going to say it's 90 degrees at the Earth's surface. Now in summertime, because the lower ground is superheated, temperatures decline dramatically as you move up in the troposphere because the ground is superheated and the air aloft is cold. And so we're going to use, a typical environmental lapse rate for winter around here. And we're going to use that nice, easy number to subtract. We're going to say the environmental lapse rate on this summer day is 10 degrees, right, per 1,000 feet. And then we're going to have a heated bubble of air. And I've just added 2 degrees. I could have added more, but this is going to represent our bubble of air rising. Yeah, so this bubble of air is heated compared to the surrounding environment, and so it's going to take off, it's going to lift off and decrease at the dry adiabatic lapse rate. Now, we're going to have that bubble of air continue to rise. As you're going to see, it's going to stay warmer than the surrounding air. We are going to reach dew point. When we reach dew point of 81 degrees, that means we've reached 100% relative humidity inside this bubble of air. And now we're going to start to form the cloud. We're still going to have thermals rising, but condensation is occurring. And we're going to wind up converting, right, to a new rate of temperature decline. It varies 2, 3, 4 degrees. And we're just going to simply have a rate of decline of 2 degrees inside that cloud, making the cloud. So let's move up 1,000 degrees. All right. Okay, so 1,000 degrees. Summertime. All right, we have a big rate of temperature decline because it's cool aloft. So we're going to subtract, so 1,000 feet up, the temperature for still unmoving air in the troposphere is 80 degrees. Right. Okay. Now this is a much larger rate now. All right, so this is the opposite that we just showed in wintertime. Now our dry adiabatic lapse rate is a smaller number. All right, so we're just going to subtract 5.5 degrees, not 10. And so our rate of temperature decline inside our bubble of air that's rising, right, is going to decline at a much slower rate. It's going to wind up staying warmer. And so our bubble of air, right, is definitely warmer than the surrounding air. What does warm air do? It's going to spontaneously rise. All right, let's move on up to 2,000 feet. All right, 70 degrees in the troposphere at 2,000 feet. We subtracted 5.5 degrees from our 86, and we've got 81 degrees. We've reached dew point. Now, definitely the bubble of air is still buoyant. It's definitely warmer than the surrounding air. We've reached dew point, and so what's going to start to happen is condensation is going to start to occur. So we're going to create a flat cloud base, but this bubble of air is still going to rise, right, forming the cloud. And so now we've got to convert to our wet adiabatic lapse rate, and our wet adiabatic lapse rate is 2 or 3 or 4 degrees. We've just chosen to subtract 2 degrees because it's just easier to subtract. So let's move up and see what's going on at 3,000 feet elevation. All right, because our environmental lapse rate is usually large in summertime, all right, it's much colder at 3,000 feet. It's 60 degrees. We've subtracted 10 degrees. Now, right, we're inside the cloud. That thermal, is still rising and cooling, but because condensation is occurring, we're making the cloud. Heat is actually being released in that phase change. Our rate of temperature decline has gotten even smaller. And so now we're just subtracting 2 degrees. And so now our temperature difference, right, is very dramatic. Our bubble of air is so much warmer than the surrounding air. It is just going to spontaneously rise and rise rapidly. Now let's go up to 4,000 feet. All right, we're definitely much warmer. This bubble of air is much warmer than surrounding air, and it's going to just take off. And I'm going to stop it at a mile up. And so at a mile up, 5,000 feet, again, we're just subtracting 10 degrees. It's 40 degrees in the troposphere. And we're making the cloud, our cloud now at 5,000 feet. The temperature, we're just taking 2 degrees off in the cloud, is 75 degrees. And so it's much warmer than the surrounding air. And the way I've got this thing set up is that this bubble of air is going to continue to rise and rise and rise. And it's going to rise 9 miles up. It's going to rise as far as it can to the top of the troposphere, where all weather takes place. And I've created a violent thunderstorm, towering thunderstorm, not just a mile up, 9 miles tall, a towering thunderstorm. Now, the condition that I've just created in that table is called unstable air or instability. This condition dominates our summer months in Louisiana. This is when any bubble of air wants to take off, as a hot spot in a thermal, and always remains warmer than the surrounding air in the troposphere, as I've just shown you. That's unstable air and is going to spontaneously rise of its own accord. Spontaneously rise. It doesn't need to be forced like the other ways that we're going to see. All right, so you've got all of these hot spots, thousands of them, all right, and so the thermals are all rising and rising and rising and rising. So all over the place, you've got rising air, and rising air against the weight of the atmosphere creates low pressure, and so we've got low pressure, and this is convection. This is convection. This is how we create afternoon thunderstorms in Louisiana, and it's very, very common. And so technically it's called convectional precipitation, and convection means vertical movement of air, and that's what we've got. We've got all of those thermals allowed to rise of their own accord. All right, and so you need to know unstable air. So let's take a look of the thunderstorm cloud of convection and unstable air. Right. Now, convectional T-storms are thunderstorms, and the name of the cloud, the thunderstorm cloud I'm going to introduce you to, is called a cumulonimbus cloud. Now, it starts out as a little puffy cumulus cloud, and then it rises into a thunderstorm or a rain cloud. And you always use the root word nimbus. You always add it when you get rain out of a cloud. Nimbus means rain in Latin. So it's a cumulus cloud that's turned into a rain cloud. And so let's take a look at the characteristics of a cumulonimbus cloud of summertime convection. This is definitely the cloud of severe weather. This is the cloud where you get thunder and lightning, you get hail. This is the type of cloud that produces tornadoes. And this is the cloud of hurricanes. And so this is definitely a bad dude, right, in terms of clouds. All right, as I've shown you in my summertime unstable air table, these clouds, these cumulonimbus clouds, if the air is really unstable, can rise to the top of the troposphere. And that's what happened in our example, our summertime example. And so here we're at the top of the troposphere, 9 miles on up. All right. Now, typically, a classic cumulonimbus cloud is kind of divided in half. One side is dominated by those heated bubbles of air rising, those thermals rising and cooling at the wet adiabatic lapse rate. And so we've got warm updrafts. These are the thermals. And so there's our dew point level, and we're creating tiny, tiny, tiny water droplets. Now, all of these thermals rising, they're rising rapidly. Because they're so much warmer compared to the surrounding environment. They're causing coalescence, all right? And it's pretty easy, to have coalescence of tiny, tiny water droplets into big raindrops if you've got thermals rising miles on up. And so usually by the time you get, 6, 7, 8 miles up, you definitely got snowflakes. You've got ice crystals. Remember, it's 60 below zero here, right? And so you've got super cooled raindrops, right? Or they're ice crystals, or they're snow. But anyway, so now they're heavy enough to now have gravity pull these ice crystals or raindrops or whatever back down to the ground, right, by gravity. And so the other side of the cloud is dominated by cold downdrafts. And remember, I mean, it's very cold up here, 60 below zero. And so you've got, the falling rain, all right, coming from very, very cold altitudes. And that's going to set up, cold downdrafts. And on the ground, just before that thunderstorm is approaching, you're going to feel very gusty winds. Cold, gusty winds. In summertime, you've noticed this. The winds will pick up, and you'll feel a little bit of a chill because these wind gusts are coming from such high and cold altitudes. And so the second half of the cloud is where the rain is going to come on down. So if it was snow up here, of course it's going to melt. And it really is very common in Louisiana when we have an afternoon thunderstorm in summertime and it's super steamy and hot, that raindrop, 9 miles up was originally a snowflake or an ice crystal and is melted. That's chances are. But anyway, so you wind up with the other half of the cloud with cold downdrafts, and this is the side of the cloud with the rain coming on down, right, with the downdrafts. All right. Now, there is a classic shape to a cumulonimbus cloud. It has what is known as an anvil top, and it's the shape of a welder's anvil. And the way you create an anvil top, it's kind of this outflow here, is in two ways. All right, it's just simply you reach the top of the stratosphere, all right, and these warm thermals rising, sometimes just can't reach into the stratosphere, and it's just the outflow, and so that outflow of the warm air is just going to pull the cloud downwind. All right, now sometimes, as is illustrated here, and those thermals rising, those heated bubbles of air, all right, are so unstable, are so much warmer than the surrounding air. They are violently rising at 100 or 200 miles an hour that they can actually penetrate into the stratosphere. And so that you've actually created clouds that can overshoot into the stratosphere. And that means that is a violent cloud. And that's what we created in our table. All right. And and there's another way too. You can have strong upper level winds, in the troposphere, and so you can have upper level winds. Just take the cloud and carry it downwind. And so sometimes you'll have a single anvil, right? And that's usually just when you've got the upper level wind carrying it, downwind. Sometimes you have a double anvil, and that's usually simply when you've got, outflow and not really any strong dominant upper level wind. Here's a picture of a beautiful example of a cumulonimbus cloud. So what's going on, below us, it definitely, is a thunderstorm and it's raining. Here are all the puffy cumulus clouds that are growing. And this is a double anvil. And we've definitely got an overshooting top. You can actually see that this is a very violent thunderstorm. Very violent thunderstorm. Let me get that thing. Oops, my phone. Sorry about that. Yeah, here's another example of a cloud, and this is a cumulonimbus cloud with a single anvil. And so there are probably some strong upper level winds, carrying the cumulonimbus, the top of the cloud, downwind. And here's just puffy cumulus clouds that are growing into a cumulonimbus cloud. Right. Okay. I did want to show you just another example of convection in summertime, and over the peninsula of Florida. So this was taken. It was a satellite image, mid-morning, and you can actually, see, the superheated land surface, the peninsula of Florida, compared to the cooler Gulf and Atlantic. So we've got all of these hot spots and thermals rising, and here's a picture a couple of hours later over Florida, and they're just choosing one of these thermals that have risen in unstable conditions and have created a cumulonimbus cloud. And it's kind of a neat picture because we're looking down on the anvil, and you can actually see the upper level winds pulling the cloud downwind. So that's kind of a neat example over Florida. End lecture 2.